Hello dear students, I welcome all the standard 10 students on this online classes. So last class already we have discussed about gravitational potential energy. Okay, where it is negative, where it is zero and where it is positive. That all thing already we have discussed and I hope all of you have understood that one. Today we will be going to discuss and learn about the derivations of kinetic energy. The formula, you know that kinetic energy is equal to half into m into v square. That formula we will derive. Okay. And one more thing also we will discuss, that is work energy theorem and types of kinetic energy. Okay. So let's start this one. Derivations of kinetic energy. We all know that one, energy possessed by an object by virtue of its motion is called the kinetic energy. If any object is moving, that means it is capable to perform some kind of work. And if it is capable to perform some kind of work, that means it contains some energy. And that energy of the moving body is called as kinetic energy. Okay. So it is measured by the amount of work done by an opposing force which brings the body to rest from its state of motion. So how can we measure this kinetic energy? Okay, so it can be measured by doing the work to oppose the motion to bring it to the rest conditions. Okay, because you know that one, if an object is moving, it must contain kinetic energy. So the amount of work is required, or the amount of work done is required to stop that moving object. So that much amount of kinetic energy is possessed by that moving object. Okay. So that's why it is written, it is measured by the amount of work done by an opposing force. Obviously, if an object is moving from left to right, then the opposing force will be acting on right to left only. Then only we can stop it. So it is measured by the amount of work done by an opposing force which brings the body to rest from its state of motion. Okay. Let us start the derivation part. Let a body of mass m moving with a velocity v be brought to rest with a uniform loss of velocity in time t. So let us consider an object or body which is having a mass of m and moving with a velocity v, and it will be coming to rest with a uniform loss of velocity in time t. So that loss in velocity, so obviously if we are trying to stop that moving object, means slowly it will be decreasing, but we have to consider here uniformly decreasing that velocity. And what is the time interval? In time interval t. Okay. Then initial velocity u is equal to v, because previously it was moving, and final velocity v is equal to 0. Why? Because we are applying the opposing force, okay, to bring it to the rest conditions. So final velocity become 0 only. So u is equal to v and final velocity v is equal to 0, and acceleration a is equal to minus a, because retardation is taking place, because the velocity of that moving object will be going to decrease. Okay. So from the equations of motions, that is the first equation of motion, b is equal to u plus at, and we have just what are the things we have taken, that one we have to put the values only. So b is how much? Final velocity 0, then initial velocity u is equal to v, then acceleration a is equal to minus a into t, or what we will get, at is equal to v, or acceleration is equal to v by t, velocity divided by time, or rate of change of velocity also called as acceleration. So from the equations we got acceleration a is equal to v by t. Okay. Now how much amount of force we have applied? So which formula we can use? Force is equal to mass into accelerations only. So mass is given, that one we have taken already as m only. So m into accelerations how much? V divided by t. So multiplying that one, we will get mv divided by t. That much amount of force applied to stop that moving object. Okay. Then average velocity while being brought to rest at that time, v divided by 2, because initial velocity plus final velocity divided by 2, that becomes the average velocity only. So here the initial velocity is v but the final velocity is 0. So v plus 0 divided by 2 is equal to v by 2 only. So distance moved is equal to how much? Yes, distance moved is equal to how much? You know that one. Velocity is equal to displacement by time, but the distance is equal to v into t divided by 2, that is velocity into time only. Yes or no? So work done in losing velocity is equal to force applied into distance moved, that is F into displacement, that is work done. So how much amount of force applied? mb divided by t into distance moved, how much distance it moved? Vt divided by 2. So after solving that one, mb square divided by 2, that is half mb square we will get. That is the kinetic energy of the moving body. So kinetic energy is equal to half into mass into velocity square. This one is the formula which already we have derived. Okay, I hope all of you have understood that one. Then the next one, work energy theorem. So what is the theorem said? It states that the work done by force on a moving body is equal to the change in its kinetic energy. So here it is written that it states that the work done by a force on a moving body is equal to the change in its kinetic energy. So how much amount of work we are applying is equal to the change in its kinetic energy. Let us learn about that one also. If a force F is applied on a body of a mass m moving with initial velocity u in the direction of motion and its velocity is changed to v, then initial kinetic energy also we can calculate and final kinetic energy also we can calculate. Yes, because previously it was moving with a with an initial velocity u, and after sometimes after applying the force F, it is moving with another velocity, that is the final velocity v also. So initial kinetic energy we can calculate, that is ki is equal to half mu square. Yes, when the velocity is u only, and the final kinetic energy kf is equal to half mb square, because the velocity at the final time or after applying the force, the velocity becomes v only. So half mb square only. And change in kinetic energy, how can we calculate? Final kinetic energy minus initial kinetic energy, that is equal to half into m into b square minus e square. Yes, so according to the work energy theorem, work done on the body is equal to change in its kinetic energy. So W is equal to half m b square minus u square. It is proved. Okay, and this one is the work energy theorem. Okay, then the next one is the types of kinetic energy. So depending upon the type of motions, different motions are there. Yes or no? Depending upon the motions of different object, accordingly it is divided into different types of motion. So accordingly kinetic energy also it will be divided. Yes, so it is divided into three types. First, namely translational, rotational and vibrational kinetic energy. So let us learn about translational kinetic energy. So the energy possessed by a body moving in a straight line is called the translational kinetic energy only. So if an object is moving along a straight line, then it becomes translational motion, and you know that one, if any object is moving, that contain energy, and that energy is kinetic energy only. So the energy possessed by a body moving in a straight line is called the translational kinetic energy. So for example, a car moving on a straight road and a freely falling body possesses translational kinetic energy. Simple one only, this one. Okay. Then the next one, rotational kinetic energy. Exactly same, rotational motion. In case of rotational motions, that object will be moving. Yes. So at that time the energy possessed by the body is called as rotational kinetic energy. Let us know about that one. So the energy possessed by a body due to its rotation about an axis is called the rotational kinetic energy, because we know that one, rotational motion means if an object is moving around a fixed axis, then it is called rotational motion. So the energy possessed while it is moving in a rotational motion, at that time that energy is called as rotational kinetic energy. So for example, the earth rotating about its axis and a rotating wheel of a moving vehicle possesses rotational kinetic energy. We know that one, earth is not only revolving around the sun, but it is rotating around a fixed axis. Okay, so that one is the example of rotational kinetic energy, and wheel of a moving vehicle possesses rotational kinetic energy. One axle will be there around which that tire will be rotating. Yes. So this one is about rotational kinetic energy. Then the next one, vibrational kinetic energy. So the energy possessed by a body due to its vibrations, yes, or motion is called the vibrational kinetic energy. So in case of vibration also we can say that one vibrational motions, yes, or in that case also that object is moving, and we know that if any object is moving, that contain kinetic energy only. So in this case that becomes that vibrational kinetic energy. So for example, atoms vibrating about their mean positions in solids possesses vibrational kinetic energy. You know that one, all the solids, inside that solid atoms are present, and that atoms are vibrating about their mean positions in solids that possesses vibrational kinetic energy. So it may happen that a body may possesses more than one type of energy at a time. It is possible at a time two types of energy a body can be possessed. For example, wheels of a moving vehicle possesses translational as well as rotational kinetic energy, because if an object or if a car is moving along a straight road, that means translational kinetic energy must be present, and because it is moving along a straight road, obviously that translational kinetic energy will be possessed by the wheel. At the same time it is rotating, that means rotational motions also present. So the rotational kinetic energy also present. Yes. So for example, wheels of a moving vehicle possesses translational as well as rotational kinetic energy. Moreover, diatomic or triatomic molecules rotate about a fixed axis along with translational motion, and hence they possesses rotational as well as translational kinetic energy. Okay, I hope all of you have understood this much. Yes, again you must go through your book. Okay, thank you.